everybody, getting ready to do lesson 7.8 part 1, pre-calculus math today, classwork lesson. My email is animatedpowerpointmathvideo at AOL.com for questions or materials for this course. Okay, so 7.8 applications of matrices and determinants, part 1 here. And you got 8 points here that'll go into your notebook. Either you have a notebook guide or into your notebook. And then 46 points here will go on your classwork sheet. If you need classwork sheets, email me for those. Students, put your name and date. If you're in my classroom, put your period here as well. And today's bell work. Hooray! Today's bell work. Find the general form of the equation of the line that passes through these 2 points here. You got this set and that set. The general form. And teachers, give your students about 5-6 minutes for that. Pause your video and see you back in 5 or 6 minutes. Okay, welcome back now for our solutions to today's bell work. We have -1, 5, 7, and 3. Find the general form of the equation of the line that passes through these 2 points here. So for 41, what we would do, we need our slope here. Here's our slope calculation. And we have y minus 5, so we have y minus y1, which we're going to call this x1, y1. So this would be y minus 5 equals our slope calculation here, 3 minus 5, 7 minus a -1. Or rather, they're doing it the other way here, -1 minus a 7 and 5 minus 3. Is the way they're figuring that. They're calculating that. So anyway, this is our slope calculation. And then, so we have y minus 1 equals m times x minus 1. So in this case, it'll be x minus a -1 would be x plus 1. So this comes out to -1 over 4 times x plus 1. So when we go through, we multiply through here. We get rid of our fraction over here. We end up with 4y minus 20 equals -x minus 1. And then we end up here with 4y plus x. We move this x over. And then we move our 20 over onto the other side. 4y plus x equals 19. And then we move our constant back over on the other side, and we have x plus 4y minus 19. So that'd be an acceptable response to 41. And then for 42, again, we have y minus y1 equals m times x minus x1. So here's our x1, y1. So y minus a -6 will be y plus x equals m. And in this case, m will be 10 minus a -6 over a -2 minus a 0 and times x minus 0. So x minus 0, here's our x1 here. And this will come out to equaling 8x here. This will equal 8 here. 10 minus will be 16 over -2 will be a -8. So we have y plus 6 equals -8x. We move our 6 over to the other side. We have y equals -8x minus 6. And then we move it back over again. Okay, this will be an acceptable general form here. So we end up with 8x plus y plus 6 equals 0. Okay, so moving into our first slide here, area of a triangle. In this section, you will study some additional applications of matrices and determinants. The first involves a formula for finding the area of a triangle whose vertices are given by 3 points on a rectangular coordinate system. So the area of a triangle, for example, with vertices at x1, y1, x2, y2, x3, y3 is like this in a determinant form here. Area would equal plus or minus 1/2 times our determinant here, where the symbol plus or minus indicates that the appropriate sign should be chosen to yield a positive area. So if we don't deal with negative areas, we got to deal with positive areas. Finding the area of a triangle, example 1. Find the area of a triangle whose vertices are 1, 0, 2, 2, and 4, 3. Here it is here. And your area is this area there. So what do? Begin by letting x1, y1 equal 1, 0 will be here. x2, y2 equals 2, 2. And then x3, y3 would equal 4, 3 out here. Then to find the area of the triangle, evaluate the determinant by expanding along rule 1. So what we're going to do here is we got x1, y1, 1, x2, y2, 1, x3, y3, 1, and then this translates into this 1, 0, 1, 2, 2, 1, 4, 3, 1. So when we have that, we're going to start here. So we have 1 times negative 1. We're going to use our formula now for finding determinants. 1 times negative 1 squared, and then 2, 1, 3, 1. So that'll be 2, 1, 3, 1 here. These will be blocked out. We're going to use this as our first element here of finding our determinant. And then plus 0 times negative 1 cubed would be 2, 1, 4, 1. So 2, 1... 4, 1, so 2, 1, 4, 1. This will be blotted out here. 2, 1, 4, 1 plus 1 times negative 1 to the 4th power would be 2, 2, and then 4, 2, 3 here. 2, 3, and then 4, 2. So we block that out, and then here is our 4 elements here to determine our determinant here on our third element. And then when we simplify these and add these together, 1 times negative 1 plus 0, this will be 0, plus 1 times a negative 2 here, negative 1. We got 6 minus a 8. That'll be 1 times negative 2. So this comes out to a negative 3. Using this value, we can conclude that the area of the triangle is, in this situation, what would it be? Negative 1/2 times that. So it'll be negative 1/2 times negative 3 would be negative, or rather positive 3 over 2 square units for the area of this triangle. Okay, we're going to move into our first guided practice here. In these exercises, use a determinant to find the area of the figure with the given vertices. So for 5, here they are. For 6, this is your independent practice. Here's your vertices here. So how will we go about doing this? Well, for 5 up here, this would be our matrix here to find our different determinants to add together to form our general determinant here for this matrix here. And then our 1/2 is out in front. We're finding the area of a triangle. And then here are our calculations here derived from our vertices here, 1/2. And then we have negative 2 here times 3, 1, 5, 1. So 3, 1, 5, 1 here. This will be blotted out. That will be blotted out. And then we come up with that calculation. And then negative 4 here would be our next one here would be 2, 1. So it'll be 2, 1, and then negative 1, 1. So see, this will be blotted out, and then see 2, 1. See 2, 1, negative 1, 1, negative 1, 2, 1. So this will be blotted out, that will be blotted out. So we have our negative 4 out in front here. And then for our third determinant here, it will be 1 out in front. And then we have 2, 3, negative 1, 5. So we have our our 2, 3 here. In this situation, negative 1, 5, negative 1, and then 5. 2, 3, 2, 3, and then negative 1 and 5. And then when we come up with that, we have negative 3. We'd have 10 minus 3 would be a 7 for that. And then this is what we would come up with here. 1/2, we have 1/2 out front. Then we have -2 times a -2. So this would be 3 minus 5 would be -2. And then -4 times 3. So it would be a -4 times 2 minus a -1 would be 3. And then this one here would just be a 1 here. So it would be 10 minus a -3 would be positive 13. And then when we add all these together, we have 1/2 times 5 would equal 5/2. So the area would be 5/2. So that would be our area here for this triangle there. Okay, so moving on to our next page here, page 6, collinear points. What if the 3 points, say in example 1, had been on the same line? What would have happened had the area formula been applied to 3 such points? Will be an inquiring question there. The answer is that the determinant would have been 0. Consider, for instance, the 3 collinear points of the 0, 1, 2, 2, and 4, 3, like this line here. These will be collinear as shown. The area of the so-called triangle, we got 3 points here, that has these 3 points as vertices, is what? It would be 0 here, right? So here are 3 points here, 1/2, and then here's our determinant here. We have 1/2 times 0 times -1 squared. We have 2, 1, 3, 1, 2, 1, 3, 1, and then plus 1 times a -1 to the cubed would be 2, 1, 4, 1, 2, 1, 4, 1. So that would be 1 out here. And then that'd be this one. And then this one here would be plus 1 times -1 to the 4th power. It would be 2, 2, and then 4, 3. So 2, 2, and then 4, 3. 2, 2, 4, 3. And then when we add all those together, we have 1/2 of 0 minus 1. See, 0 minus 1 times -2 plus 1 times -2 would equal 0 for that one there. So this result is generalized as follows. Test for collinear points. 3 points x1, y1, x2, y2, and x3, y3 are collinear. That means lie on the same line, if and only if this determinant here will equal 0. That would be the way that you would tell that they are collinear. Okay, moving off now into our next example. Example 2, testing for collinear points. Determine whether the points -2, -2, 1, 1, so -2, -2, 1, 1, and then 7, 5 are collinear. Are they collinear is the question. So we begin by letting x1, y1 equal -2, -2, x2, y2 equal 1, 1, and then x3, y3 equals 7.5. Here they are there. And then once we know that, we have our graph here showing those plots. Then by expanding along row 1, you have this situation here, x1, y1, x2, y2, x3, y3. And then we plug in our values here. We end up with this matrix here to find our determinant. So -2 minus, so our first blot out here is blot this, blot that, and we end up with a 1, 1, 5, 1. And we have our -2 out front, so -1 squared times our mini determinant here, plus -2. Again, now we blot this out, and we blot this out, so we have a 1, 1, and then a 7, 1. So we have our -2 here out in front. Then we have -1 cubed times this. And then for our last row, we blot that out, and we end up with a 1, 5, 7, 1. And then we have this one out front here, multiplied by -1 to the 4th power. And this will yield us negative 2 times negative 4 plus 2 times negative 6 here, and then plus 1 times negative 2. When you combine all these together, you get a negative 6 here. Okay? Because the value of this determinant is not 0, you can conclude that the 3 points are not collinear just by doing that test. And let's try one here. Use a determinant to determine whether these points are collinear up here. Here's yours down here, students. Do that one yourself. We'll do this one up here. So for this one up here, our points are 3, negative 1, 0, negative 3, 12, and 5. And then here is our determinant here. And then when we add all these together using our formula that we've been using earlier, we end up with a 0 result here for our determinant. This means that the points are indeed collinear. Cramer's rule. So far you've studied 3 methods of solving a system of linear equations. That is, substitution, elimination with equations, and elimination with matrices. You will now study one more method, Cramer's rule, named after Gabriel Cramer, 1704-1752. This rule uses determinants to write the solution of a system of linear equations. To see how Cramer's rule works, take another look at the solution described at the beginning of section 7.7. There was pointed out that the system, this system here, has a solution. Well, okay. A1x plus B1y equals C1. A2x plus B2y equals C2. So if it has a solution like this one here, x, we can divide our C1b2 minus C2b1 over A1b2 minus A2b1. So we can use this quotient here. And from this we get y equals A1c2. So we change this here, A1c2 minus A2c1 over A1b2 minus A2b1. So we shift these around. Our quotient for y is different than our quotient for our x, provided that A1b2 minus A2b1 does not equal 0. So it cannot equal 0 in that case down here. This cannot equal 0. And we're using this as a quotient for each one of our y and our x, if you notice that. So our numerators are different here. C1b2 minus C2b1, and down here it's A1c2 minus A2c1. Each numerator and denominator in this solution can be expressed as a determinant as follows. So here, x would equal C1b2 minus C2b1 over A1b2 minus A2b1, which would equal this 2 matrices here as our quotient, and then for a y, we have A1c1 over, A2c2 over A1b1 and then A2b2. So we do have the same matrix in our denominator. We just change our matrices up here for our numerator. Relative to the original system, the denominators of x and y are simply the determinant of the coefficient matrix of the system. This determinant is denoted by d. The numerators of x and y are denoted by dx and dy, respectively. They are formed by using the column of constants as replacements for the coefficients of x and y as follows. So here's our coefficient matrix here, and then our d is here, our dx is here, and then our dy is there. So our C1 we shift here. Dx is C1 C2 over B1, or rather B1 B2, and then for our dy it'd be A1 A2, and then we have C1 C2 over here. So these swap places here for our x and y. For example, the given system 2x minus y equals 3, negative 4x plus 3y equals 8. With that system there, the coefficient matrix d and dx and dy are as follows. So our coefficient matrix would be here, and then d would be here, dx would be here. So we have 3 and negative 5 and 8 and 3, and then our dy will be 2 and 3, and then negative 4 and 8. So these shift over here. Cramer's rule generalizes easily to systems of n equations and n variables. The value of each variable is given as a quotient of two determinants. The denominator is the determinant of the coefficient matrix, and the numerator is the determinant of the matrix formed by replacing the column corresponding to the variable being solved for with a column representing the constants. For instance, the solution for x in the following system is shown. Okay, so moving forward with this, here is our matrix here, our first system here. B1, B2, B3, you know, so they're over here. Then A11, and then A12 would be here like this. This would give us our x3 would equal A3 over A. So both of these are matrices over each other here in our numerator and our denominator. And how we get these formulations here will be determined by this original system. So Cramer's rule: if a system of n linear equations in n variables has a coefficient matrix A with a non-zero determinant A, then the solution of the system is x1 equals A1 over A, then x2 will be A2 over A, and on and on and on to xn will be an over A. So that will be Cramer's rule there. Where the ith column of A is a to the I is a column of constants in a system of equations. If the determinant of the coefficient matrix is 0, then the system has either no solution or infinitely many solutions. Okay, well, let's try some of this. There's a lot there to digest. Using Cramer's rule for a 2x2 system. Use Cramer's rule to solve this system here. Here's our system here. So to begin, find the determinant of the coefficient matrix. So our coefficient matrix would be what? So we have 4, negative 2, 4, negative 2, 3, and negative 5. So our D would equal that. And then our determinant here will be negative 14 for our coefficient matrix. Because this determinant is not 0, I'll apply Cramer's rule. So when we apply Cramer's rule, our d of x here will be 10, negative 2, and then 11, negative 5 over negative 14. So we found this to put in our denominator. And then we put this down here, 10, and then 11 over here. And then we kind of oppose that to our coefficients for a y here, negative 2 and negative 5. And then when we do that, when we do our cross multiplication there, we have negative 50 minus the negative 22 over negative 14. This comes out to negative 28 over negative 14, which equals 2. And then for dy, we have 410. And then 311, so 410, and then 311. It's almost like when we have a y here, now we go to our x coefficients over negative 14. And then we do our cross multiplication here. We have 44 minus 30 over negative 14. We come up with 14 over negative 14, which equals negative 1. So the solution is x equals 2 and y equals negative 1. That's pretty cool. Check this in the original system, and yeah, it comes out. So let's try one now. Use Cramer's rule to solve, if possible, this system here of equations. So to do this first one up here, we end up with our negative 1, 11. So negative 1, 11, and then 9, and then negative 9 here for our x. And then for in our denominator, we have our coefficient matrix down here, which comes out to, negative 90 over 30, which equals negative 3 for x. And then for y, we have negative 7, and negative 1, and 3, and 9 over, again, our coefficient matrix here, negative 7, 11, 3, and 9. This comes out here to negative 60 over 30, and this will give negative 2 here. So by using Cramer's rule, our solution will be negative 3 and then negative 2 for this system here. And that is 7.8, part 1, pre-calculus math. Here's my email, animatedpowerpointmathvideo@aol.com, for course materials or any other questions. Thank you very much.